Hello, my name is Sergey Paltsev, and I'm a director of the Energy at Scale Center at MIT, and I'm also a senior research scientist at MIT Energy Initiative and deputy director of the MIT Joint Program on the Science and Policy of Global Change. It is my pleasure to participate in the Applied Energy Symposium and to share our research on hard-to-abate sectors. In particular, I'm going to explore our understanding of the role of industrial carbon capture and storage in emission mitigation. I would like to start with setting up a big picture which shows the challenges which lie ahead of us. In the diagram, you can see the growth in emissions over time starting from 1965. And you can see that the majority of the emissions are coming from 4 world regions. It means that we really need to find the solutions both in those 4 regions, but also the solutions which are going to work in the rest of the world. Due to the current pandemic, the 2020 estimate shows a reduction between 4 and 8% of the global carbon dioxide emissions. These are dramatic reductions which would need to be sustained, but without hurting in the economy if we really want to reach the decarbonization targets. And part of those emission reductions are coming from so-called hard-to-abate sectors. So the industrial emissions from those sectors are coming from 2 different channels. Part of those emissions are related to combustion. When we are combusting coal, natural gas, oil for heat purposes and other purposes, we are releasing CO2 in these industrial sectors. But part of the emissions are coming from non-combustion. So when we use those fuels as a feedstock, and that part of the emissions is also substantial. And whenever we are looking at the pathways to decarbonize hard-to-abate industrial sectors, we need to take into account both of these types of the emissions. The diagram which I'm showing now provides you the relative shares of these emissions both globally and in major regions, the major emitting countries. You can see that the emissions from industrial processes are about 10% of the global emissions. And you need to add about 20% of the emissions from combustion processes. That shows you that the contribution of these sectors to CO2 emissions are quite important, and it is extremely important to find the solutions for reduction in emissions. The chart which I'm showing now provides you an illustration that in order to reach the targets which countries have agreed at the Paris Agreement process need to be accelerated. And so those reductions are extremely important because we need to start reducing now, and we need to continue those dramatic reductions over time for a substantial amount of time. And by the mid-century, we need to approach net zero emissions. Depending on the development of the negative emission technologies, such as BECCS, which stands for biomass energy with carbon capture and storage, or direct air capture, or other negative emission technologies, the steepness of the reductions might be slightly different, But regardless of that, we know that in comparison to the current trends, the decarbonization efforts has to be dramatically increased. What we also know that those decreases has to be at the unprecedented pace. And the graph which I'm showing right now shows the historic emissions which I showed previously and the level of reductions which are required to reach those aggressive goals of limiting the increase in global air surface temperature no more than 1.5 degrees Celsius. The current pandemic is already changing the profile, and the big question is how we are going to be and where we are going to be at the end of this current pandemic. And if history is of any guide, we can take a look at the emissions with global financial crisis in 2008, where global emissions also have reduced, but then they pick up and then they start increasing, and the trend for increasing emissions has been continued. We really need to change the way how we are getting our energy in order to break that trend, in order to change the profile and decrease the emissions by the mid-century. It's not only about the carbon dioxide. Other gases are also important. And it's not only about the fossil fuels and electricity and heat production, because other sectors are extremely important. So this diagram provides you relative contributions from different gases and from different sectors. And what we need to do, we need to reduce all of these emissions down to zero. Currently, number of governments, both local and national governments, companies, other jurisdictions, other institutions are providing pledges for net zero targets by mid-century. That means that we need to eliminate all these sources in order to achieve those net zero greenhouse gas emission targets. Such aggressive reduction create a lot of challenges, but also create a lot of opportunities for scalable low carbon options. And it's not about technologies. It's not about economics. It's not about geopolitics. It's about all of them together, because the solutions need to be viable both in terms of the available technologies, in terms of the economic competitiveness, but also they need to coincide with other goals which society has. So decarbonization is a really important goal, but it's not the only goal for us. We also need to make sure that we are reducing poverty, we are reducing income inequality, that we are dealing with the public health issues, we are dealing with a lot of other negative aspects which are extremely important for the welfare and well-being of our planet. And so whatever solutions we will be able to find has to work both technologically, also geopolitically, and also we need to make sure that the new solutions are not bringing the new environmental problems, but they are reducing the current environmental problems, not only in terms of the climate change, but about other aspects like the water quality, air pollution, and other aspects which are related to the environment. Now I'm going to turn to projections of the fuel use in these hard-to-abate sectors in the industrial park. And what do I mean by the hard-to-abate sectors? It's numerous industries where the heat requirements and feedstock requirements are such that they are hard to replace with alternatives. So that's why they called hard-to-abate sectors. So the examples of those sectors are iron and steel, chemicals, cement production, fertilizer production. So all these would require the solutions globally in order to make that contribution. Currently, a lot of action is happening in the power generation and transportation sector. And so we already know the options. We already know the relative costs of these options. It is much less action and much less understanding of these hard-to-abate industrial sectors, which we also need to deal with, because we need to reduce those emissions to zero from every corner of the economy, from every plant, from every facility. We have to be at zero. And as you can imagine, that's not an easy task. So the diagram which I'm providing right now shows the projections from the International Energy Agency from their latest World Energy Outlook. Those outlook is pre-COVID, so that outlook was released in 2019. And obviously, well, now all projections need to be adjusted to make sure that we are taking these new trends which were imposed by global pandemic, how they are going to affect the development of the economy and how they are going to affect the development of particular sectors. One thing to note right away is that it's a lot of fossil fuels which are used as energy in these sectors. And even in the sustainable development scenario, which is quite aggressive scenario where the policies are imposed much more aggressively in comparison to what we have currently under the Paris Agreement, even then you see that it's hard to decarbonize. So by 2040, we still have substantial share of coal, natural gas, and oil in the energy use in the industry. And the electricity, which is shown here in the red color, you also see that that's a quite substantial part of the energy requirement in the industry. And the question is how to decarbonize electricity as well, because if this electricity is still fossil fuel based, then that is not going to provide the full solution. So it's a combination of the emission reduction in the sectors and those energy inputs from other sectors, which also has to be decarbonized. In terms of the long-term understanding of the structure of industries, of the structure of the decarbonization pathways, of the structure of the solutions which would lead to decarbonization, right now it's even more uncertain and even more challenging to make those projections, because a lot of structural changes after the current pandemic may stay with us, may even increase. And so we are going to see very different ways of how we work, how we travel, how we shop. And that all affects the demand for industrial sectors, and that affect where we are going to see the development and where we are going to have additional funding, additional support for decarbonization in these hard-to-abate sectors. And it's extremely important because we can find some cheaper technologies which may work in a subset of the applications. But in order to really decarbonize, we need to find those solutions which are going to be applicable to wide coverage to all the regions, and we can have positive spillovers from one sector to another sector. Unfortunately, the impact of the COVID already shows that that task is going to be even more difficult, because currently we see that the companies, the countries are starting thinking about the prioritizing resilience over efficiency. What that means, that they want to protect supply chains. They want to protect a situation where borders are closed and that immediately affect the supply chains of particular industry or particular company. It means that we will see more and more movements away from globalization, and that means slow growth, and that means that we are going to have less available funding to make that economic transition, to make that low carbon energy transition. And so those transitions are going to be even more challenging in comparison to what they were seen before the current COVID pandemic. It means that we need to take a look at all of these pathways in their interlinkages, and we need dynamic modeling for interconnected systems. And that's exactly what we do at our MIT Energy at Scale Center. I encourage you to visit our website, and you see the link on information about of our website here. And please get familiar with the research topics which we are pursuing. And we are covering a lot of aspects of different aspects which are related to the scaling up of the action. We are looking not only on the technological issues, but we're also assessing the economics and environmental impacts which are related to these different pathways to global decarbonization. We have a lot of experience and we have a lot of tools which we're employing for our analysis. We are looking not only on the energy and economics, we are looking at how those choices are affecting the earth, how those choices are affecting the physical impacts. So we are looking at both the transitional impacts of climate change from different pathways, different policies, but we are also providing understanding for the physical impacts that those choices are inflicting from different pathways and different policies which we may choose. And we're also trying to understand how different regions are affected in different ways, because the answers for, let's say, India or China or Africa or the United States or the European Union might be quite different. In order to understand these policies, these choices in terms of the technologies, we are employing our multi-sector, multi-regional model, which was developed over the course of the couple decades. And we are constantly improving and enhancing this model, where we are also tracking not just the technologies, but also trying to understand what is the impact on the overall economy, what is the impact on international trade, how the energy mixes in one region may affect the choices in other regions. And so we can understand, if we are imposing, let's say, renewable portfolio standards, what is the impact, what is the economic impact, not only on the electricity and power generation market, but wider impacts on the whole economy in that particular regions, but also in its interlinkages to other sectors and other regions. In terms of the hard-to-abate sectors, we are mostly looking at the following options for decarbonization. Carbon capture and storage, or CCS, is one of the most important pathways for decarbonization, and that is required by introduction of particular policies to support the carbon capture and storage. Without those policy supports, either as a mandate or standards or carbon pricing or emission trading, the carbon capture and storage is not going to be economic. And so what we are trying to understand is what kind of policy support are needed, where we can remove those barriers, how we can speed up the development of particular pathways. And so, as I'll show you later in my presentation, well, CCS plays a key role for the decarbonizing hard-to-abate sectors. In combination or by itself, electrification is another important option. So some processes are easier to electrify, some processes are more challenging to electrify, but we also try to understand what are the options in these different sectors. Hydrogen is extremely important in making sure that we have viable pathway for removing emissions from hard-to-abate sectors, but hydrogen is only as clean as the way how hydrogen was produced. So if it comes from low carbon or carbon-free sources, and in some cases that means that we need to employ CCS on hydrogen production, then we have the solution of the low carbon energy system. But currently, hydrogen is mostly produced in so-called gray way. And so that gray hydrogen, well, means a lot of emissions. So if we are producing hydrogen from steam methane reforming from natural gas, or we are producing from coal, then that process actually is very emission intensive. Biofuels, also an important option where applicable. And again, those requirements for high heat in some industries, they work better. In some industries, they not work as good yet. And so we are trying to understand what is the role of biofuels. Material substitution. So for example, if we will find new, let's say, construction materials, and you don't really need cement industry as much as before, well, that is going to affect the emission implications in these different pathways. And obviously efficiency improvements. Those are extremely important to make sure that we are constantly making processes better and better and better, because that immediately results in savings of energy, in reduction in emissions. Well, the problem is to look at these hard-to-abate sectors. That's a really heterogeneous representation. And so even within the region, we have numerous plants with very different characteristics. And when we are looking globally, when we are comparing different regions, those impacts and the contribution and the technologies which are employed in different regions are even more heterogeneous. And so our approach is to focus on so-called marker industry, where we are trying to understand what are the options in cement production or iron and steel production or chemicals. And so then we are applying that to similar type of the facilities which are related to this marker industry. I already have mentioned that extremely important to distinguish between the energy inputs and feedstock inputs in the consideration. I'll provide some of the potential, some estimates of the potential for emission reduction in several industries, and then I'll show the results when we put that into our global multi-regional, multi-sector model. Well, what are the implications? How big of the impacts? What is the cost of different options? And again, we are still in the process of understanding that. So those illustrative results, which I'm going to show, already will provide you good understanding what are the options, what are the trade-offs, what are the costs. And that is what we are constantly improving and still pursuing in our understanding. So the information on this slide shows you what are the reductions in the CO2 emissions can be done with different options for steel production. And you can see that even improvement in the efficiency of the existing basic oxygen furnace already provide you 15 to 20% reduction in the emissions. Use of biofuels or use of the other process, direct reduced iron, where we can combine that DRI process with electric arc, also provide substantial emission reduction. Closer to the topic of my today's presentation, the use of CCS is also extremely important, but you can see that that's not really the full solution, at least if CCS is employed only on the blast furnace. So another consideration which we are taking when we are trying to understand what are the pathways for steel, iron and steel making industry is try to understand how much we are producing from the primary production, so directly from iron ore, versus how much steel is produced from scrap. And so this consideration is extremely important when we are making our projection. In terms of the CCS employed on steel production, there are several options which already exist and several potential options which are also extremely important to understand and explore further and to develop further. The first commercial CCS facility on a steel production plant has been built online since 2016 in Abu Dhabi. So Abu Dhabi CCS project captures 0.8 million tons of CO2 per year. And those emissions are captured from the DRI reactor, and then those emissions are transported by CO2 pipeline for enhanced oil recovery. So you remember that I have mentioned that CCS needs support, and this enhanced oil recovery provides additional funding in order to make the economic sense of this particular facility and in general. So it means that we need to find other policy support, or we need to find the value for the product after we captured that carbon. And so we can try to find that value for, in this case, enhanced oil recovery, or in fuels, in materials, in other ways. Also, there are other innovative steelmaking processes which produce flue gas with high CO2 concentrations, which already attractive for CCS, because that's already reduced the cost of the CCS application. Extremely important is to understand how steelmaking plants are behaving when hydrogen is used for high temperature heat. And again, the word of caution, I already mentioned that, well, in this pathway, hydrogen is only clean as the way how it was produced. But that offers another very interesting, very important avenue for decarbonization of steelmaking. Turning to another hard-to-abate industry, cement production. We also looked at different pathways and different options for decarbonizing that industry. The current amine technology requires steam. And so in this diagram where I'm illustrating the process of cement making, well, we don't really see a steam making process. So it means that if we really want to use the amine technology for capturing carbon, we need to employ an additional unit where we would generate steam. So this diagram shows that addition of steam generation and carbon capture with a amine-based technology, which currently is the most promising technology, the most advanced technology to this point, which can be employed in the cement industry. And it can capture up to 90% of the carbon emissions. And again, well, we need to make sure that, well, the steam requirements are adequate for this production process. At the same time, we need to also explore other ways which at this point may be not as developed in comparison to the current CCS technologies, but they provide a lot of promise that we may do the capture in much more economic way, but we still at the early stage of development. And one option which I'm providing here is cryogenic carbon capture. And I'm providing additional link for additional information. The beauty of this process is that this process only uses electricity. So there is no requirement for that additional fuels for steam generation. And so this process potentially, when you just don't have that parasitic load, potentially that may imply substantial economic benefits and substantial economic competitiveness to alternative ways to capture. So we have done the estimates, what would be the cost reduction if we will go post-combustion route versus cryogenic route. And again, the technologies are at very, very different levels of the current development. But potentially you can see that if we will go cryogenic capture, so CCC route, the costs are dramatically lower in comparison to the post-combustion route. Immediately, that has a lot of implications for trying to assess what is the future of these energy-intensive, hard-to-abate sectors. In this diagram, I'm showing you that without carbon capture, the energy-intensive sectors has a very hard time under the decarbonization policy. Because, well, the cost which is going to be imposed on these industries are going to increase the cost of the products dramatically, that the demand for them is going to reduce also substantially. So these diagrams, very illustrative diagrams, shows you the importance of the CCS, and under the 2-degree or even more dramatic 1.5-degree policies, we can see that that's deployed quite substantially. And if we are going to have more aggressive targets, well, that deployment is going to happen even earlier than that. This diagram also provides you the impact on the economic cost of median target with CCS or without CCS. And as you can see, those increases can be quite dramatic. Also, we can take a look which sectors are decarbonizing faster and which sectors are decarbonizing slower. These diagrams with a dark blue area shows you that hard-to-abate sectors, they critically need the CCS. Otherwise, it's going to be much more expensive to get us to the full decarbonization. And again, these scenarios requires full decarbonization by the end of the century, but you can imagine the increase in challenges if that decarbonization is required by mid-century, by 2050. Well, I already showed you some diagrams where I show that if we want to resolve the issue that how to make sure that we are at net zero by sometime 2050, 2070, some period of time, we need to find the solutions for this hard-to-abate sector. And so that's exactly what we are doing in our research, where we are looking at different technologies which are already out there and technologies which are promising. And we put that into our tool where we are analyzing not only how that technology is doing by itself, but how that technology interacts with other technologies. And so what is the portfolio of options which are bringing us to the required net zero world in order to mitigate the impacts of the climate change. And some answers we already know, but a lot of answers which we still need to discover. And so that's why this symposium is extremely important, because that provides a look at all of these options, at all of these technologies, the solutions, the policies, the interactions of them, how to find the solution for decarbonization. And so again, I'm encouraging you to take a look at what we do and contact us if any particular questions. We are more than happy to interact and show what our current findings are, how we can help to solve the issues or questions which you might have. And so only by this working together, solving these challenging problems, we will be able to decarbonize hard-to-abate sectors and other sectors, and we are going to really make the difference in saving the planet. Because after all, that's the only planet which we have, and we need to make sure that we are preserving that, not only for us, but for our children, for our grandchildren, and for many generations after that. Thank you very much for your attention. It's my pleasure to be involved in this symposium, and it's my pleasure to provide you with the information on what we are doing in this area. And please contact me if you have any particular questions. I wish you to stay healthy, and I wish you all the best. Thank you very much for your attention.